so close to the end now, it's got to feel good. We just have 2 more sections left. Of the 2 sections, this is probably the harder of the 2, but I hope it's not that hard. The next section is word problems, but they're really friendly word problems. In this section, we're going to need to do a lot of prime factor trees for numbers, and my calculator does prime factor trees pretty well if I put it in the right mode. So I'm going to get my calculator just in the regular mode 1. Right now I was just graphing because I did section 7.1 last. And regardless of what your screen has showing on it when you turn it on, if you hit the mode button and select option 1 for computation, that's probably the mode you're going to want to be in, probably for the rest of the chapter. We won't have to worry about any complex numbers or i's coming up. So a lot of the beginning problems in section 7.2 I can look at and know the answer. Every problem in section 7.2, it has an equal sign, and my goal is to find a value for x that makes each side of the equal sign reduced to the same number. And I'll do the problems even if I can do them in my head using algebra, because the algebraic technique I'm going to use is going to work kind of regardless of how complex the problems are, whether I can do them in my head or not. So first of all, you might know just the answer to number 2 is 3, because I'm trying to find a number that I can replace with the x so that both sides of the equation come out to be the same number. And anytime I write an answer to a problem that has an equal sign, I can check. To check would mean to go to the original problem, replace the x in the original problem with the number or numbers you think are the right solution, and then simplify. So I'm going to simplify this by just going 3 exponent 3, and I get 27 equals 27. Doesn't help you if you don't know how the answer by just looking at it. For most every problem in this section, I'm going to find the prime factoring of any non-prime numbers to solve them by hand. 27, I'm going to do a prime factor tree. I'm just going to go 27, hit the equals button, and then shift, and then this factor key. And it says 27 is 3 cubed. So I can rewrite problem 2, leaving the left side written as 3 to the x, rewriting the right side as 3 cubed. And the trick to this section is there's a theorem that says if each side of an equation has the same base, then you can solve the problem by dropping the bases and setting the exponents equal to each other. So my goal for most every problem in this section is to take the initial problem, rewrite the problem so that both sides have the same base, and then if I can get the bases the same, then I can drop the bases. In this case the bases are 3's, and set the exponents of x and 3 equal to each other. And that's why 3 comes out to be the answer algebraically. Of course, the problems are going to be harder than that as we get deeper into this, but not crazy hard. 4, I could also look at it and know the answer. The answer to 4, and hopefully some of you can just rock that without doing any algebra. The answer is going to be x equal to 2, because if I tried to check that, I'd go to the original problem and go 4 squared equals 16. I'd change the x to 2, and I know that 4 squared is 16. The way I'm going to solve this algebraically is not going to look near as nice as the last problem, because I'm going to do it properly. And the proper way to do it, the non-clever way to do it, I guess I'll say not necessarily the proper way, but just kind of the way that most of these problems will be done unless you see a shortcut. The non-clever, non-shortcut way to do this is to do a prime factor for every non-prime number. So 4, if I do a prime factor tree for 4, I go 4 equals, and then shift enter 4. Shift factor. 4 is 2 squared. So I can rewrite the left side, and I can replace the 4 with a 2 squared. And when I do that, it's going to turn out that the exponent of x gets multiplied by the exponent from the 2 squared. And so I threw a parentheses in that probably really wasn't necessary at this stage, but you kind of have to think of this like this. This is 4 to the x power, which is 2 squared to the x power, and then I multiply the exponents. Now I'm going to do a prime factor tree for 16. 16 is 2 to the 4th. And what I've managed to do, taking 3 steps where maybe I could have done it in 1 step, is I was able to write each side with the same base. And if I can write each side with the same base, I can drop the bases and set the exponents equal to each other. I'm going to do a bunch of these where I have to use parentheses and multiply exponents, so don't worry if you didn't catch it this time through. You'll be a pro quicker than I was able to become a pro at this kind of stuff. So same strategy, but slightly more complicated. You could have, if you were clever, if you knew that 16 was 4 squared, you could have just done this. And of course, if you knew that, you probably would have just written down the answer. But you don't have to necessarily make each base a prime number. But my calculator, if I'm going to use it for factoring, is going to give me prime numbers. And had I solved it this way, making both the bases 4, you can drop the bases and set the exponents equal to each other. It's a little bit slicker, but in certain contexts, you have to be way more clever. 32, I know what the answer is, but you may not. So I'm going to write 32 as a power of 2 by going 32 equals shift factor. If I couldn't write 32 as some power of 2, then I would need something called logarithms to solve this problem. And we no longer cover logarithms in intermediate algebra. We used to, but we don't anymore. The fact that we don't cover them means I can't set a problem up so that it's impossible to write both sides with the same base. 2 is a prime number on both sides, so that's probably the nicest way to rewrite them. Now I have the bases set equal, so I'm going to drop the bases and set the exponents equal. I'm just going to minus 1 from both sides, and my answer is going to be x equal to 4. And of course I can check. The nice thing about this section is there won't be any extraneous solutions. To check, I'd take the x that I think is correct, which is 4, plug it into the original problem, and simplify. To simplify 2 to the 4 plus 1 power, break out my calculator. My calculator tells me that this breaks down to 32 equals to 32, so I know I'm good. 3 is a prime number, so I can't on number 8 do anything to the left side. 243 is not a prime number, which means I can prime factor it. So 243 equals shift factor. 243 is 3 to the 5th power. So it's kind of a tricky problem, but it's not horrible. But you might, if you worked ahead of me, you might have gotten stuck, and that's okay. Once you see the trick, you probably won't get stuck on it again. So for now, I've got the bases the same, which means I drop the bases and set the exponents equal to each other. And now I'm going to minus 5 from both sides. And this gives me minus x, and I'm going to emphasize minus 1x equals 0. To solve for x, I need to divide by the number in front of the x, which is negative 1. On the left side, the negative 1's cancel, and I'm left with an x. On the right side, I have a fraction with a 0 in the numerator, and fractions with a 0 in the numerator are equal to 0. Again, I always can check these. To check these, I go back to the original problem, replace the number I'm using for x into the x in the original problem, and then I break out my calculator because I check so much more accurately and quicker on my calculator. And this would give me the left side reduced, and it equals the right side, so I know the answer is right. 10's a little bit trickier, and again, if you're moving ahead of me, I love it when you do that, but you might have got stumped. 27 we factored on problem 1, it's 3 cubed, and I'm going to treat problem 10 like this. I'm going to think of this as 27 to the x equals to 3. Anytime the number that has the x attached to it isn't prime, before I do the prime factoring, I put it in a parentheses. And now the prime factoring for 27 is 3 cubed. And then I'm allowed to multiply the exponents because there's one base raised to 2 exponents. So I'm going to multiply the exponents. And of course, the 3 written to the right of the equal sign, it doesn't have an exponent, so there's an implied exponent of 1. So I took 3 steps to take that original problem and make it so the bases are both 3's. Now that the bases are both 3's, I can set the exponents equal to each other, divide by 3, and I believe my answer is 1/3. The nice thing about the calculator that we use, it's so easy to check. I should just go, is 27 to the 1/3 power equal to 3? Yank this thing out, do 27 exponent fraction 1/3, and see, it's really frustrating that it's hard to make the calculator show up, but it does give you 3, and it makes it so I know that 1/3 is the correct answer. 12 is just like the problem 10, because the number that's attached to the exponent isn't a prime number. I'm going to put it in a parentheses, and then I'm going to prime factor it. And you could prime factor on your calculator. 49 is 7 squared. And just like the last problem, I'm going to multiply the exponents on the left side to get rid of the parentheses. And on the right side, I need to pop in an exponent of 1, because if there's a number written without an exponent, there's an implied 1. And now I'm going to set the 2x equal to 1, divide both sides by 2, and get my answer of x equal to 1/2. And I'll skip checking this. You can check it yourself by going and confirming that 49 to the 1/2 power equals 7. And if you do that on your calculator, it'll give you that, because 1/2 power is the same as square root. So this is like saying the square root of 49 equals to 7, and it is. Ooh. This is in some sense evil, because I think I have to be clever. I didn't realize that I stuck a problem in here that required you to be clever. Because if I tried to do the prime factoring of 36, if I did 36 equals shift factor, 36 is 2 squared, 2 squared times 3 squared. That's not so nice, because the trick that I've been using only works real nicely if both sides can be made into a prime number. And 36, its factoring isn't just one prime number, neither is 6. So what I'm going to try to do, and hopefully this isn't overly clever, but I guess you're going to have to be a little bit clever, is I need to write both sides with the same base, and 36 is 6 times 6. I guess I just have to know that because the square root of 36 is 6, that I can rewrite the left side with the 6. Sorry, I didn't realize that I snuck something a little more advanced in here. This is the first time I'm lecturing on this. I wrote the problems about a month ago, and I just forgot that I snuck that in there. So I'm doing this just like the last 2 problems, but the prime factoring of 36 wasn't going to help me, and I want to get something so that both sides have the same base. And because 36 is already 6 to some power, I'm going to rewrite 36 as 6 squared. My calculator doesn't tell me that 36 is 6 squared when I do the prime factoring for it because it gives me 2 squared times 3 squared. So the method that I've been using, because the numbers were perfect squares, worked fine. When the number's not perfect squares, you have to be a little bit creative, and I can't imagine I made the problems where you have to be super creative. So now it's going to be even trickier yet. So I have both sides with 6's. I need to clear this parentheses. I clear the parentheses by multiplying the 2, that's the exponent of the 6, by the x plus 2. And at some point I need to get an exponent on the right side, and I'm going to put 1 there. And now I'm going to multiply the exponents and clear that parentheses. So this gives me 2x plus 4 equals 1 because I have the bases the same. So I'm going to minus 4 from both sides. That's going to give me 2x equals minus 3. And then I'm going to divide both sides by 2. And that gives me x equals minus 3/2. And I better check that because this was a pretty slick problem. I would suspect we'll get more of these slick problems. I can't imagine just giving you one of these. So for checking, I want to see if 36 to the negative 3/2 plus 2 power equals to 6, because that's what it takes for this problem to work. I go to the original problem, I plug the answer in for x that I think is the answer, and then I check. So let me do the left side. So 36 exponent fraction negative 3/2 plus 2. Looks enough like the original problem that whatever my calculator gives me, it better be 6. If it's not, I've made a mistake. And since it is 6, I didn't make a mistake and I did it right. Okay, 16, both the 1 and the 2 are prime, but it's a horrible fraction. So I'm going to have to do something to get that fraction doctored up, because the fraction's making bad things happen for me. I also need to deal with the 8, and the prime factoring for 8 is 2 cubed. Not sure you can see it, but so the 8 is 2 cubed, which is nice because on the right hand side I see 2, but unfortunately I can't just say x equals to 3 as the answer, because that's not the case, because you could only drop the bases and set the exponents equal when both sides have exactly the same base. The trick for dealing with fraction bases is to take the reciprocal and change the sign of the exponent. So we had a rule for if we had a fraction with a negative exponent, we can flip the fraction and make the negative exponent positive. I'm going to use that rule in reverse. I'm going to flip this and change the x to negative x. The reason I'm going to do that is because it gives me a base of 2 on the left-hand side, and this is using the reverse of a rule that we've used a bunch of times so far this semester. So I'm going to rewrite the left side as 2 over 1 to the negative x, and I'm going to leave the other side at 2 cubed. The nice thing about the 2 over 1 on the left side, 2 over 1 can be just written as 2. And to clear the parentheses, I just need to attach the exponent to the 2. We did that a few times earlier this semester. So the 8 was the easy side to deal with. When you have a side that's a fraction, you can get rid of the fraction by flipping the fraction, making the exponent negative. That is, if it's a 1 over fraction. And now I'm to the point where I can make the exponents equal to each other. That negative x is, I think of as a negative 1x. Don't usually write the 1, but it helps me on this step if I do write the 1. And the answer I believe to be right for problem 16 is x equal to negative 3. I'm going to check it. For checking, I'm going to make sure that 1/2 to the negative 3 power equals to 8. If I was doing it by hand, 1/2 to the negative 3 power is 2 over 1 cubed, which is 2 cubed, which is 8. But I'll check it on my calculator because it's way easier. So on my calculator, parentheses, fraction, 1 over 2, parentheses, exponent, negative 3, and you get 8, which I need for a correct answer, because my answer is only correct if when I go to the original problem, put my answer in for x, I get a true statement. But I do the same thing for 18 that I did for the last problem. Do a prime factoring for 27. The prime factoring for 27 is still 3 cubed. And I'm going to work the same trick on the right side. So the fraction isn't helping me because it doesn't match up with the 3 that I get on the right side. So to take a fraction that has a 1 in the numerator, you can flip it over and eventually get rid of the fraction if you change the sign of the exponent. So the flipping and changing the sign of the exponent gives me 3 over 1 to the negative x equals 3 cubed. 3 over 1 is equal to 3. And 3 to the negative x, you can just attach the negative x to the 3 and drop the parentheses. And just like I did for the last problem, I'm going to throw a 1 in front of the x when I drop the bases, just so it makes it easier to see what I need to do. And my answer to this is going to be x equal to negative 3. And again, I'm going to check it. I'm going to check to see if 1/3 to the negative 3 equals to 27. So parentheses, fraction, 1 over 3, parentheses, exponent, negative 3. And I get the 27 that I was supposed to get. So I know that my answer is correct. And I can move on to the next problem. And hopefully it's more of the same, because I'd like to do more than 2 of these. Oh, it is more of the same. So 20 is a lot like 18, which was a lot like 16. I'm going to prime factor 125. And the prime factoring for 125 is 5 cubed. You might be able to skip some steps if you get good at these. The other side I'm going to write as 5 over 1 to the negative x, which is just 5 to the negative x, and I don't need the parentheses anymore once I'm done with the fraction. And then I set the exponents equal to each other. That's when I introduce the 1. All these are equal to negative 3. I get my answer of x equal to negative 3. I won't check this one, but it'll check again if you care to. Okay, prime factoring for 32 first. 32 is 2 to the 5th. And I'm going to work on the right side. I'm going to make it 2 over 1 and then flip the sign. I need to find the opposite of this. When it's just a single x, you just make the x negative, which is finding the opposite. When it's an x minus 3, I go the opposite of x is negative x, the opposite of negative 3 is positive 3. So when you're flipping it over, you're finding the opposite if it's more than just a single x. Now this is the same as 2 to the negative x plus 3 equals 2 to the 5th. And I don't need the parentheses anymore. I could just attach the negative x plus 3 to the 2 without the parentheses. It has the same meaning. Drop the 2's and go negative 1x plus 3 equals to 5. I'm going to minus 3 from both sides and get negative 1x equals to 2. And then divide by negative 1. I believe my answer is x equal to negative 2, but I absolutely should check that just because it's not terribly hard to check, and it keeps me from making a mistake. So for my checking, I need to make sure that 1/2 to the negative 2 minus 3 equals 32. Could do that by hand. This would be 1/2 to the negative 5 equals 32, which would give me 2 over 1 to the 5th equals 32, which would give me 2 to the 5th equals 32, which would give me 32 equals to 32. But I like checking with my calculator. It's quicker, probably more accurate most of the time. So parentheses, fraction 1 over 2, parentheses, exponent negative 2 minus 3, and you get 32 equals to 32. The nice thing about this calculator is any teacher will let you use it in a class higher than this. When I teach like Math 151 and Math 142, which are kind of the next classes after this, there's some things that this calculator can't do that a graphing calculator you need for. I make my students have a graphing calculator, which can be rented for $20 for the semester, but most of my students that have had me for this class will use this calculator for most everything and use the graphing calculator for the few things that this calculator can't do. Because this calculator doesn't graph, there's some things that it has some limitations. 24, same sort of problem. I'm going to write this as 3 over 1, and then I'm going to write the opposite of the exponent. The opposite of positive x is negative x. The opposite of negative 4 is positive 4. I'm going to prime factor the 9, which I could do in my head. And then I'm going to skip the steps. I'm just going to write this as 3 to the negative x plus 4. Those steps that I had been showing, the 3 steps to get there or 2 more steps to get there, you don't have to show those. Now I'm going to drop the 3's and go negative 1x plus 4 equals to 2. Go to minus 4 from both sides and get negative 1x equals to negative 2. And then divide both sides by a negative 1 and get x equal to 2 for an answer. Doesn't feel like a horribly long video, so I'll go ahead and check this. To check this, I need 1/3 to the 2 minus 4 to equal to 9. So parentheses, fraction 1/3, parentheses, exponent 2 minus 4, and you get 9 equals to 9. So it literally takes 10 seconds to check. On a test, I'd probably 100% check because I don't want to write down a wrong answer, so I might as well check. Same sort of deal for 26. I'm going to write this as 5 over 1. I'll take the opposite of the exponent. The opposite of positive 2x is negative 2x. The opposite of negative 1 is positive 1. And we've done 125 just recently. You could do it on your calculator if you don't know that it's 5 cubed. It is if you do a prime factoring for 125. Now I'm going to drop the 5's and set the exponents equal. Minus 1 from both sides and get minus 2x equals to 2, and then divide both sides by negative 2 and get x equal to negative 1. I won't check this one, but you can check it if you want to. (28), the right side, the 16's not prime, so I can sneak it inside of parentheses and do its prime factoring. And its prime factoring is just 2 to the 4th, which is a good thing. I don't have to do anything cutesy on this one. And again, you can use your calculator if you don't have the prime factorings memorized. Now I'm going to multiply the exponent on the right side to clear the parentheses that I put in. It's going to give me an exponent of 4x minus 16 on the right side. And now I'm going to set the exponents equal. I'm going to go 1x equals 4x minus 16. And then I'm going to go minus 3x minus 3x minus, I'm going to go minus 4x minus 4x, which will give me minus 3x equals minus 16. And then I'll divide by minus 3. And my answer, I believe, is positive 16 over 3. I'm worried about that for an answer. So I'm going to check it. I'm going to, on the left side, see if 2 to the 16 over 3 power equals 16 over to the 16 over 3 minus 4 power. I think these are going to be horrible decimals, but it's okay. So for the left side, 2 exponent fraction 16 over 3. I'll write just a couple decimals. This is 40.31747. And then hopefully the right side comes out to be the same. So the right side, 16 exponent fraction 16 over 3 minus 4. And I get that same number. And because I got the same number for both sides, then the answer is correct. So I don't care what each side reduces to, as long as when I put in what I think the answer is for any x in the problem and reduce, both sides have to be the same number. In this case, is one of the rare problems where both sides had an x, which means I needed to make both sides, plug the x in and both sides reduced. For 30, I need to think of the 25 side as being in a parentheses before I prime factor the 25. 25 is not a prime number, so I know I need to prime factor it. And I'm going to make this 5 squared to the x plus 6. And you can do the prime factoring for 25 on your calculator if you need to. Now I'm going to clear the parentheses on the right side by multiplying the exponents. Eventually I want a 1 in front of the x on the left side. It's just going to make my work easier. And I was able to multiply the exponents. You get 2 times x, which is 2x, 2 times 6, which is 12. So this gives me 5 to the 1x equals 5 to the 2x plus 12, which gives me the ability to go 1x equals 2x plus 12. And then I'm going to minus 2x from both sides. 1x minus 2x is negative 1x. And then I have to divide by negative 1. I believe the answer is x equal negative 12. This is going to be a real challenge to check because I think my calculator is going to go into some horrible scientific notation because it's a really small number. So I want 5 to the negative 12 to equal 25 to the negative 12 plus 6. And like I said, it's going to be a challenge. It's not going to be a challenge for my calculator, but it's going to be a challenge for me to just do the checking because it gives me a funky answer. It gave me this, 4.096 times 10 to the negative 9th power. And if I want to write that without that times 10 to the negative 9th power, I'd have to take that decimal and move it 9 places to the left. So I'd get a point and then 8 decimals 409. But I don't need to do that. I just need to do the right side and hopefully get exactly that. So 25 exponent negative 12 plus 6. I get the exact same thing. I don't care what each side reduces to, as long as each side reduces to the same number, I consider my answer correct. It doesn't have to be a very pretty number, and it definitely wasn't there. Hmm. 32. 3 is a prime number. I don't really need to worry about it so much. The 27 is not a prime number. I'm going to throw it in a parentheses. Then I'm going to do the prime factoring for 27. And again, I can do that without my calculator because I've done it enough times that I just know what it is. And then I'm going to be a little bit slicker on the next step. I'm going to just clear the parentheses and multiply the exponents on the right side. And I'm going to go 3 times 5x and 3 times 4 and make 3 to the 15x plus 12. Now both sides have the same base, so I set the exponents equal to each other and drop the 3's. No factoring yet because there aren't any squares. So I'm going to get minus 1x from both sides to get the x's, positive and on the right side, and minus 12 from both sides to get the numbers on the opposite side from the x's. On the left side, when I minus 1x, it cancels the x. 1 minus 12 is negative 11. On the right side, 15x minus 1x is 14x. And on the right side, the 12's cancel. Now I'm going to divide by 14 and divide by 14. And I'll get my answer of negative 11 over 14 equals x. I could write x equals negative 11 over 14. I'll skip the checking, but you're welcome to check again. It's just a matter of going to the original problem, changing both of the x's, and doing each side separately. And again, I probably reduced to a funky number. 34, I leave 7 to the x minus 1 on the left side, introduce my parentheses on the right side. The prime factoring for 49 is 7 squared. And now I'm going to multiply 2 times x and 2 times 4. And get 7 to the 2x minus 8. And I set the exponents equal to each other. I snuck a 1 in front of the x because it just helps me. And now I'm going to minus 1x from both sides to avoid having negative x's, and add 8 to both sides to get the letters and the numbers on opposite sides. On the left side, when I subtract 1x, the x cancel. Negative 1 plus 8 is positive 7. On the right side, 2x minus 1x is 1x, and the 8's cancel. My answer is 7. Let me check it. It takes 2 seconds. So to check this is 7 to the 7 minus 1 power equal 49 to the 7 minus 4 power. So left side, 7 exponent 7 minus 1, 117649, and the right side, 49 exponent 7 minus 4, exactly the same number, and that's what I need for a checking to have validity to make sure my answer is right. Both numbers in 36 are not prime. They both need to be popped into a parentheses. They both are multiples of 5 or powers of 5, so it's not so bad. The prime factoring for 125 is 5 cubed. Again, you could do that on your calculator if you don't have it memorized. The prime factoring for 25 is 5 squared. Now I'm going to multiply the exponents and drop the parentheses. On the left side, you're going to get a 3x. On the right side, the exponent's going to be 2 times x and 2 times 6, which is 2x plus 12. Now I'm going to go 3x equals 2x plus 12 because I have both sides written with the same base, so I can set the exponents equal to each other. Now minus 2x minus 2x, and that gives me an answer already of x equal to 12. Parentheses on the left side because the 81's not a prime number. I don't need to do anything to the right side because 3 is a prime number. The prime factoring for 81 is 3 to the 4th, which is good. Again, if I can't get both sides to have easily have the same base, then I need something called logarithms to solve the problems, and we don't do those. So every problem in section 7.2, there's supposed to be a way that's not too terribly hard to make each side have the same base. Now I'm going to multiply the exponents, 4 times x and 4 times 1, and get 4x plus 4. Now I'm going to set the exponents equal to each other. I'm going to minus 4x and minus 4 from both sides. On the left side, everything cancels and I get a 0. On the right side, 5x minus 4x is 1x. I think the answer is x equal to 0. That doesn't mean no solution, it just means 0 is the number that works. I better check this. This is an odd answer. So for checking, I need to find out if 81 to the 0 plus 1 power equals 3 to the 5 times 0 plus 4 power. I can do both of these in my head, but I won't try to show off. So 81 exponent 0 plus 1 is 81. And the other side, 3 exponent 5 times 0 plus 4 is also 81. So both sides reduce to 81. I don't care what number both sides reduce to as long as they reduce to the same number. Both numbers in 40 need to go in parentheses because neither is prime. Nine is 3 squared. 27 is 3 cubed. I'm going to multiply the exponents to clear the parentheses. On the left side, I go 2 times x, which is 2x, and 2 times minus 1, which is minus 2. And on the right side, I multiply 3 and 5x and get 15x. Both sides now have the same base, so I drop the bases and set the exponents equal to each other. I'm going to get a negative x because I want to get the x's on the opposite side from the number. So I'm going to minus 2x from both sides. Well, I guess I'm not getting a negative. That's going to give me negative 2 equals 13x. And then I'll divide both sides by 13 and get negative 2 over 13 for an answer. Hopefully these are feeling very repetitive. Other than that problem with the 36 and the 6, it was like one of these things is not like the other. The rest kind of fit the same mold, and like to think that on the review that's the mold I'll stick to. 625 is 5 to the 4th power, believe it or not. 625 equals shift factor 5 to the 4th power. And so I'm going to rewrite this and that side with the prime factoring. 625, I'm going to replace it with 5 to the 4th. 25, I'm going to replace it with 5 squared. I'm going to multiply these exponents to drop the parentheses and get 5 to the 4x. Multiply 2 times x and 2 times 6. Get 5 to the 2x plus 12. Drop the bases, set the exponents equal to each other. And then minus 2x minus 2x. That gives me 2x equals to 12. Divide by 2, divide by 2, and my answer is going to be x equal to 6. So we just have one more section for the entire semester. We'll have a review too, but one more section of new material. They're all word problems, but they're really friendly word problems. So don't be intimidated by them. Just go into that section with an open mind, and hopefully you'll come out of that section just knowing that I'm not BSing you. These are going to be easy word problems. It'll be a nice way to kind of end of the semester. And hopefully this whole chapter is kind of a nice way to end of the semester. Sections aren't that long. First section of graphing, I use my calculator to do the tables. Here, the problems are all just variations of each other. They're all real similar. And that's going to be the same. The word problems, the problems are all kind of feel, hopefully, tolerable by the time we get done with them.